Okay guys, so I'm in Chicago, so we don't have class, and I'm just going to give you some of the lecture that I was going to give on Monday. Alright, so we're going to talk about equation of state mixing rules. You're going to need this for project 3. And I'm also giving you a homework assignment to kind of get you on track for project 3 that's going to be due next Monday. Homework assignment is described on the last slide. Okay, so you've seen this PV diagram. It's for a pure component. You guys should be familiar with this by now. And we've used this equation of state. This one's SRK. But we want to apply it to mixtures. So what do we need to do? Well, we're going to assume the mixture behaves just like a pure fluid. We do that. It's called van der Waals one-fluid theory. So we have the same equation of state that's going to describe the behavior of our mixture that we had for the pure components. But what do we need to do this? Well, we need to calculate the A and B parameters for the mixture. A is going to be a function of temperature again, just like before, and B will just be a function of critical properties. And you can see them in the equation of state at the top here. So how are we going to calculate them? Well, we're going to use mixing rules, and I'm going to present some of the basic mixing rules on the next slide. Okay, so the one version of mixing rules that you can use. I'm going to present them here, but first we need to start using arrays for everything. It will make your life a lot easier when you actually implement this. So first off, we're going to assume that you have a vector of the mole fractions. So I wrote it in general here. So x1 is the mole fraction of component 1 all the way through xn. So here's the simple example mixture of basically 3 components, AA, BB, and AB. It doesn't matter what they are, but basically if they had those mole fractions, the vector of mole fractions would look like I've written down here at the bottom. So you want to basically adapt your programs to take vectors for the mole fraction, because you're going to need that. So go ahead and do that. The other thing you need is basically the expressions for the mixing rules. So these are the simple mixing rules that van der Waals proposed using. You can use these or other mixing rules, but I'm just going to show you the simple ones. So just look in the literature for other examples. So the B for the mixture is basically a weighted average of the pure component B's. It's weighted by mole fraction. So here you can see it's just the sum of all the pure component B's times their mole fraction. So that one's pretty simple to understand. It's basically an average. If you look at the A for the mixture, though, it's a little bit more complicated. It's a quadratic mixing rule. So I'm going to show you how to implement that on the next slide, but this is the expression for it. This ChE is known as a binary interaction parameter. You don't need to use it now, but it's essentially used to force phase equilibrium results to match data. So it's totally empirical. You can't calculate it based on any kind of theory, and it's basically an adjustment parameter to make things fit better. If you look at the original paper for SRK that Suave did in 1972, he shows results using the ChE and not using it, and you can see that you can use it to adjust and make the phase envelope fit much better. So something you probably want to look into because you need to do that in your project. So just keep that in mind. Okay, so I put together some tips for you to actually implement this. So like I said before, you want to start using arrays for everything. So your critical properties, this is an example for 3 components. So now you'll have a vector or an array of critical properties. So first element could be the critical temperature for component 1, and then the critical temperature for component 2, and so on. And you probably want to do the same thing for PC and omega as well. So now, for example, as arguments to your SRK function, instead of having scalars that are TC, PC, omega, you're going to have vectors, most likely. That's probably the simplest way to do that. And also, now you're looping over components, so you probably want to start to actually use loops in your programs. If you don't, it's going to be really tedious, and you're going to be repeating yourself a lot. and you basically want to make it so that it doesn't really matter how many components there are. You can just use the same piece of code to do everything. So I've given you some almost working code. You have to figure out the rest on the right here. So basically, the calculation of the mixture B is all set. It's a weighted average of mole fraction. Just double check it. Make sure you understand what's going on. A is a little bit more complicated, and I didn't give you the whole answer, so you'll have to figure it out. It's got this scary double loop going on, but if you have questions, just let me know. So you'll need to implement these. All right. So here's a flow of the calculations that you're going to use when you start to do mixtures. So you already know how to do the first one. So you're going to calculate the pure component A and B using critical properties. And then you're going to calculate the A and B for the mixture using the mixing rules that we just defined. And then you're going to calculate the dimensionless A and B, the capital A and capital B, the same way that you did for pure components. So you guys already know how to do this. And then you just plug it into the same EOS and solve for the vapor and liquid compressibilities. And from there, if you want to, you can get the volumes. If you have questions about that, let me know. Okay, so this is your homework for next week. You need to pick mixing rules that are appropriate for your equation of state and system. So look into the literature, figure them out. A lot of you can just use the simple mixing rules that I've presented here, but you might find that there are some that are better suited for what you're working with. Then you have to go and dig and find some experimental liquid and vapor density data for a mixture that's comprised of any two components from your chosen system. So you don't have to do all of the binaries in your system. Just pick two that are convenient, find some data for them, and then obviously you probably know I'm going to ask you to compare to that data. So take the data, do the calculation with your US and compare the results, and then let me know how accurate it is. Make some kind of plot or just do something to show how it performed over the range that you looked at. And that should make sense. So if anything's not clear, if you have any questions, just ask me or work on it with your classmates, and try not to do this the night before again. Again, this is needed for your project, so this will get you on the right track.